Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with the last lesson of chapter 2, and we're going to do a little bit more with graphing. In the previous lesson, we talked about scaling so that we can graph and how we choose the numbering system for our x and our y axis, our horizontal axis and our vertical axis can affect the spacing and how our graph looks and how easy it is to read. Okay, so today we're going to take some real world types of situations and we're going to plot those data onto coordinate grids and learn a little bit more about some strategies for graphing and scaling and how to interpret the graphs. This lesson, you will use all that you know about graphs to solve challenging graphing problems. Each of the situations in this lesson will require you to think hard about what a graph tells you and what the best way is to show it. As you work to solve these problems, think about what makes the task challenging. Focus on how you can get yourselves unstuck if your teacher's not immediately available. Oh, that's right there. That's where you're working in groups. And one of our goals is, as we go through this program, is for students to try and figure things out within their groups, asking each other questions, seeing what seems logical, and not immediately raising your hand to have the teacher come and help the moment something looks challenging. The reason why we do this is because someday you're not going to be in school anymore and you're going to be responsible for solving problems, and you might be on your own and have to figure something out, or you might be with a group of people and you can talk about things to try and figure it out. But one thing that I've noticed when I'm like in my backyard trying to fix something that I've never worked on before, I can raise my hand and no one's coming to answer my questions. Okay? You've got to learn how to start figuring things out. And we understand you're in middle school, and sometimes even in your groups when you've had a good discussion, there might be disagreements, and I will come over to help students and answer their questions. But eventually you get to that point where, okay, we've got to do what we think is best, and you got to practice that way of thinking. So that's what this statement is about. That we know that you are not sitting in groups right now because you're doing this at home, and so we'll just talk about it together, you and me me on the video. Okay, so Andre works in his family's juice shop. He has invented the new Mathberry Madness smoothie, and word is getting around. He wants a graph showing how many new smoothies have been sold throughout the first month. He has gone through the cash register records and gathered the data for some of the first 12 days. And this is the data that you see at the right, and you should copy this data down, put it into your journal. He wants to graph his data and use it to predict approximately how many berry smoothies he can expect to sell by day 20. Okay, so we've got day 3, 4, 6, 9. So he's got the first 12 days of data, and you can kind of see, and these are smoothies sold per day, not the total number of smoothies. So day 3, he sold 3 of them. Day 4, he sold 5. Day 6, he sold 10. So you see that number gradually going up. First, between day 3 and day 4, he sold 2 more, but then he doubled his sales by day 6 and then doubled it again by day 9. And so this doesn't necessarily look like it's a straight line trend. This looks like it's going to curve, right? Well, at least I know that. You may not know that because you don't have as much experience graphing. Okay, so here's your task, and notice that there's a stoplight here. Where has there been a mistake made? So examine Andre's graph. Here it is. Can you use it to predict how many smoothies would be sold by day 20? And so I'm looking at the graph, and I'm looking at what we learned the other day was scaling. It's like, what's his counting sequence on his x and his y axis? It looks like he's just taking those data points from this table and just decided, I'm going to have these be my numbers on my x axis and this be my numbers on my y axis. But that's not how our scaling works. We can't do that with number lines. So the question is, what is the next one supposed to be? Are we counting by ones? Are we counting by twos? Are we counting by threes? Looks like we're counting by ones again, then by twos. Does that mean that this has to be a 15? What about here? 3, 5, 10, 20. There's no pattern to it. And so it's not possible. Stop it. What did I just do there? There we go. It's not possible because our scaling is unpredictable. So that's one of the reasons why you need to have proper scaling. Count by threes, count by twos, count by ones. Whatever you choose to count by, it's got to be consistent throughout the entire axis, for the entire graph, okay? So what we're going to do is we're going to change the scaling of our X and our Y axis. Now you've got your journal, you've got something you're doing your work in. Remember I said in the other day how it's better if you have graph paper. I highly recommend you do this work on graph paper. If you have a journal that does not have coordinate grids like this, is not graph paper, but you do have graph paper on the side, I'd recommend you do your work on a graph paper and then cut it out and glue it in, paste it into your journal so that you can use it as reference later, okay? So I'm going to turn the page here, and I would recommend that the days count by twos or threes, or if you've got the room, you can count by ones, but we need to get to day 20, right? Because that's what the question is asking us, is to predict approximately how many smoothies will be sold by day 20. It's important that our number of days on our graph make it to the number 20 day. So I decided to count by ones here, but you may not have room. You may decide to count by twos. However you want to scale that is up to you. And then for the number of smoothies, I honestly don't know how high it needs to go. So I'm just giving myself plenty of room for the number of smoothies on the y-axis. Notice how on the 12th day, it was 38. And it's not really counting by twos or threes. It's really starting to jump here, right? Here it jumped by 10, then by 8, then by 10 again. And so it seems like getting it up into the 80s or the hundreds or even up to 120 like I did seems like the best way to go. So you decide how you're going to create your graph. Pause your video. If you haven't already copied this down, make sure you copy it down and then create a graph and then plot each one of these ordered pairs. And I'll just remind you that we're putting the days on the x-axis. So the number for the day is going to be your x, and the number of smoothies sold will be your y for each of your ordered pairs. Okay, so 3, 3, 4, 5, 6, 10, 9, 20, 10, 28, and 12, 38. Find the x value first, then go up to the y value and plot those points. Unpause when you're ready to continue. All right, I'm going to remove this and I'm going to show you what my graph looks like. I started off by plotting each one of these points. Here's the 3, 3, the 4, 5, the 6, 10. This is 9, 20. This is 10, about 28, and then 12, 38. Okay, now what I'm noticing here is there seems to be kind of a line, a trend where it's starting to go up, right? And so it doesn't look like we're like going flat here and then starting to trend up and then it should go flat again, right? If it's trending up here the entire way, we want to continue with that trend. So that's how I drew this line. This is a non-linear kind of a situation in that it doesn't form a straight line. It forms kind of curve, but the trend is going to continue with that curve most likely. So our goal was to try and approximately predict on day 20 about where that line would be, and it looks like it's somewhere around 100. So if we're going to make the prediction here, show where on the graph you would expect to place a data point for day 20 and explain how many smoothies are likely to be sold by then. Ooh, sold by then. Maybe it is the total number of smoothies sold. I don't know. I think it's per day. So the trend line on the graph shows that on the 20th day, about 100 smoothies should be sold. Okay, so that's what we do is we take data points, we plot those data points, we look to see if there's a trend, and then we extend that trend using a line of best fit, and then we make predictions along the way. So, if I wanted to go and say, okay, how about on the 16th day? That looks like it's going to be about 70 smoothies. What about on the 14th day? That looks like it might be about 50 to 52, 55, somewhere in that area. What about on the 18th day? That looks like it's going to be somewhere around 85 or 90. Are these absolutes? Absolutely not. They're predictions, but they're based on the trend that we are seeing for the first 12 days. So we would expect that trend to continue. Now, someone might argue, well, you're never going to sell like a million smoothies. So at some point, it's got to level off, right? If you're in business for 10 years, right, this is only the 20th day selling it. But after 10 years, you at some point, it's got to level off. That's absolutely right. But let's just look in short term, not overall long term. All right, so now graphing challenges. Don't even bother reading this. We're going to do both of them together. I'm not assigning different challenges for different students. Let's just do two different situations. So here, a table to the right shows the time it took 5 different students to get to the mall and how far they traveled to get there. Okay, so the distance in miles is listed here. They're not in any particular order. And the travel time in minutes is listed here. So, in this situation, I think it's prudent to make the distance in miles be our x, because the way that we set this up, typically time shows up on the horizontal axis. It's, I'll talk in 8th grade about how the x variable is your independent variable, and that's what you have control over, and the y value is affected by whatever x is. You don't have as much control over this. So figuring we're probably going at a constant rate of speed, the distance that you are from the mall typically will affect how long it takes you to get there. So we don't really have control over how far we are from the mall, but this is affecting that. So we make this our X and that our Y. This our input, that our output. And once again, I'm using some terminology that you're going to hear a lot in 8th grade that may not make as much sense to you now, but I'm just planting the seed now, and then we'll go deeper into it in 8th grade. So let's go ahead and do that. Let's make our our distance away from the mall is going to affect how much time it takes. So in this situation, we're not going to make time our x value, even though that's very common. In this situation, the time is going to be on our y axis. Okay, so you can scale this any way you want. I decided to spread it out a little bit more, making each one of these lines a quarter of a mile, 1 mile, 2 miles, 3 miles, 4 miles, and we only need to get to 4.1 miles, so I didn't even bother getting to the 5th one here. And for our travel time, our greatest is 20 minutes, so I made sure that I could fit as much, so I counted by 2s here. You might be able to count by 1s, however you want to count your y-axis. Once you've got that completed, then go ahead and plot these points. Once again, we're calling the x the distance in miles, and the y the number of minutes traveled. When you're ready and you've got all these points plotted, go ahead and unpause, and we'll see what my graph looks like. All right, this is what my graph looks like. Where's the trend line? Do you see a good trend line? I mean, this is what you would call a very weak association, primarily because of this outlier right there. How many outliers can you have in your data before you decide there's no association, right? Now, the one thing, I mean, it could be, I mean, are they walking? Are they riding bikes? Are they riding the bus to get to the mall? I mean, how are they getting there? Are their parents driving them and they're being dropped off? That's the main question here. We don't have enough information to see how they're getting to the mall. Are they all walking to the mall? And why, oops, sorry, why is this person taking so long? Did they stop along the way to tie their shoe and then saw a friend and decided to have a conversation with them? So they wasted time. Is this the true trend line? Those people were all like singularly focused on getting to the mall and they walked at about the same rate of speed, but then you had two people lollygagging. I don't know what the story is for this. So it's kind of hard to make any predictions from this particular set of data. Okay, here's challenge B. To use the pool at the Columbus Recreation Center, guests must pay one annual fee and then must pay a small fee for each time they go to swim. Jeff and his 5 friends kept track of how many times they went to visit the pool in 1 year and how much money that they spent. So the number of the visits here and the cost in dollars, please copy down this table. This is a situation where it seems like everyone's paying the same annual fee, correct? And you would think everyone would have to pay the same small fee to get in. Now, what is that small fee? I don't know. When we get into higher levels of math, like 8th grade, that would be it. We could use this data to figure out what the cost is for the annual membership fee and how much they charge per visit. We could do that. But that's not really the goal of today's lesson, so we're not going to do it here today. So looking at this data, looks like the number of visits is going to affect how much money you have to pay. So we're going to make X our number of visits. We're going to make Y the number of dollars. Okay. Once again, if it doesn't quite make sense to you why we're choosing this to be X and why we're choosing that to be Y, I haven't quite taught that yet. So it's not necessary. I'm not going to test you on choosing the right axis for each one of these columns. So don't worry about that now. Let's just focus on scaling the graph and plotting the points and seeing if we can identify a trend. So I decided my number of visits needs to be up to 114. So I made my graph go up to 120 and I counted by tens. The amount of money that they spent, the highest was 149. So I needed this to go up to 150. So I decided to count by 25s to get to 150. Okay, you create the graph and then please plot those points and see if you notice a trend. Pause and then unpause when you're ready. Okay, let's see what this looks like. Wow, that's a pretty straight line, isn't it? Let's go to our farthest right and let's draw a line. And that looks like a very strong association. The reason why it's a strong association is because everybody, oh, stop it. I'm going to have to plug in for a second. Pardon me, I'll be right back. Did I forget to pause it? I'm so sorry. It must have been very boring for you. Okay, so here we are. Where did I leave off? Did you miss me while I was gone? So sorry. Okay, so what was I saying? All right, so we expect there to be a very strong correlation between these because each one of these is a different person, right? They all paid the same annual fee. They all paid the small fee to get in every time they went in. So we should be able to predict without too much trouble how much it would cost if you visited 50 times or 100 times. Well, no, we have 100 or 140 times if we wanted to extend this graph. So I could do it right now. In fact, I'm going to do it right now. I'm going to show you that there is a way, although I'm not going to walk you through the process. I'm just going to do the work and I'm going to show you an equation that matches this particular situation. So I'll be able to tell you what the annual fee is and how much they charge per visit. I'm pausing and I'm going to make it work this time. Pause. Oh, I'll do it. It's funny. Pause. Goodbye. All right. I'm not going to walk you through what I did here, but I did take 2 ordered pairs and I figured out the slope ratio, the rate of change was 1. So 1 over 1, 82 over 82, in this case 1 over 1. So that means that the small fee that they pay to get in is $1. And once I figured that out, then I was able to figure out what the y-intercept was, which is this point right there, which is 35, which means that's the annual fee. So I can now confidently declare from this situation that it costs $35 per year, and every time they go swimming is $1. And this is the rule that applies there. Plug in any of these numbers for X, for the number of visits, that's going to be $1 per visit. So this person paid $18 worth of small fees for 18 visits, $100 worth of small fees for 100 visits, and so on, plus the 35 annual gives you the total amount that they have paid, okay? And you notice this point right there, this is 25, that's 50. Does that appear to be pretty close to 35? Yes, it does. So that agrees with my calculation. Now, I would say this, there's a problem right there. For some reason, this person went 29 times, so they should have paid $64, but they paid 65. Just a little bit of a mistake that was made there. I'm not quite sure whether that should be 30 or that should be 64. Either way, it's not that big of a deal. It didn't really stop us from making our predictions. Okay, so now you can predict if you go 40 times, you would expect to pay $75. Let's see if that works. What is 40 plus 35? That is absolutely $75. Okay, so this is where you're going to be going. This stuff right here, after you've mastered what we did today of graphing. All right, now this is the last problem. Jackson heard that the baseball pitchers are getting taller and taller. He found the data that is shown here at the right. I'm imagining these are Major League Baseball players. Jackson thought a graph might help him to see how the heights are changing, but he thinks that his data is really hard to graph. Do you agree with him? What would make this hard to graph? Remember how you graph your x and your y intercept, or your x and your y axis intercept and 0, 0. So can you imagine having to fit this into your either x or your y axis? I would think that this would be your x axis because we're seeing how over time heights have changed. So this is affecting that. So that's going to be your x, that's going to be your y. And so my response is, yeah, fitting these years in is really difficult. Okay. So this is what he's decided to do. Jackson has an idea. He decided to change the way that he writes the data. And he started a new table that you need to complete. So how did Jackson figure out what numbers to put into the table? Kind of looks like he decided to make 1000 or the year 1870 be year 0. Okay? So what he's doing here, Jackson subtracted 870 from every year and 60 from every height. Now, the first year is year 0. 1870 is year 0, and the year 1900 would be year 30, since that's 30 years after the very first date in which they took the average height of baseball players. And at the same time, rather than trying to worry about starting in the 60s or 70s, the heights are the height above 60 inches. So this is 9.3 above, I guess that would be 5 feet tall, right? So that's 5 feet, 9 inches tall, and then 5 feet 11, almost 6 feet tall, and so on and so forth. Okay? So what we're going to do is let's continue this. So this was 1870, this was 1900, this was 1930, and so on and so forth. Fill in these data points, making sure that you take these years and subtract 1870 from each one of them and write the answer here. And then these heights, subtract 60 from those heights, and write them there. Once you've got those written in, then go ahead and set up a graph. And I decided to make my graph go all the way up to 140 years after 1870, and our height up to 20 inches above 60 inches. Okay, so I want you to complete this task now. Finish this table, finish the graph, and then plot all the points in the graph to see if we can identify some sort of a trend. Okay, I actually have all of this done, but I need to transfer this data into my graph, so I'm going to pause, and when I unpause, we can check and compare our graphs. All right, does your graph look like my graph? Here is year 0. This would be the year 1870, where it's 9.3. Then 1900 is 30 years later, and that's about 11.4, and so on and so forth. So it looks like it, sometime around the turn of the century, around between 1870 and 1930, there was a little bit more of a steep incline, and then it started to level off. You can see that between 1960 and the year 2000, it only increased by 9/100 of an inch. Not much, almost 1 inch. No, did I say hundredths? 9/10, almost 1 inch growth here, whereas here there was a couple inch growth in just that 30-year period. So it started off a little bit sharper. And so do we expect that to level off? Do we expect it to keep going on? This would be something where at some point it's got to level off, right? Because the number, the number of years can keep going on and on and on, and we're not going to see 8 feet tall people probably in 100 years from now. So, yeah, what is 74? That's like 6'2.5", somewhere around there. So it's, you could get up to 6'3" or 6'4", but probably not going to go into the 7 feet range like basketball players. So there you go. Different things to look at. Sometimes we can change the numbering sequence to make it easier to graph. We just have to make sure we label these appropriately like we did here. Sometimes your graphs form a pattern. You can see a strong correlation between the data, and you can make solid predictions from a line of best fit. In other situations, sometimes like this one, the graph is all over the place, and maybe that line of best fit isn't as accurate as we thought because of too many outliers. Okay, go ahead and do your homework, and you can expect to see graphing popping up in our future homework periodically throughout the rest of 7th grade. And then we're really going to dig deep into this in 8th grade. It's a main part of the 8th grade curriculum. All right, take care. Bye.
Hey, feeling good.